Okay, we're
There it
recording
is.
now and we
Yep.
can see it.
Okay. Hey, hi, everyone. Well, my name's Stephen Miller. I belong to the Rose City Astronomers. I'm a member of their astrophotography special interest group. Three of us that run that group as part of the Astronomer Club. The Astronomy Club in Portland has about 1,000 members. The astrophotography group probably has 50 members. Typically, in our meetings, we have a beginners meeting and an advanced meeting. Usually have about 20 people in the beginner meeting and about 12 people in the advanced meeting. We have meetings once a month, and then we have an in-person meeting on site during our monthly general Rose City Astronomer meeting. We usually have a speaker and so forth. And there we do hands-on demonstrations and talks. And then they also have outings. You know, they have two or three dark sky locations that they do outings for. A lot of it's for astronomy too, of course, people just viewing. But then there's astrophotography goes on at those meetings too. So I joined the astronomy club probably about 4 or 5 years ago, but then joined the special interest group a couple of years ago. And so I did give a filters talk, and when Dan reached out to me, I said, "Well, I have the talk I give about the light pollution filters, but it's embedded in a larger talk. And why don't we just give the entire filter talk, even though some of it's kind of beginner material?" And he said, "Yeah, go ahead and do it." And so I'll give the entire talk, but more than half is just about light pollution filters because I'll focus on that a fair amount. So anyway, so that's what you're going to get tonight. First, a little bit about yes, tonight's presentation on deep sky filters. I have presentation on filters for planetary and solar and some of these other things, but tonight's deep sky filters. A little bit about me. So yeah, I'm a native Northwesterner. Grew up on the Oregon coast, Newport, Oregon. It's kind of a lumber fishing town. I studied electrical engineering and computer science at Oregon State, which was only an hour away from Newport, so it was easy for a small local kid to go to school there. I worked as an engineer for Hewlett Packard for 33 years. Been retired for about 8 years now, actually, this April. And my focus at HP was on imaging science. I ran a team that did a lot of our imaging science for printing. So all how rendering documents, color space conversion, halftoning, compression. I had a team of imaging software engineers. We worked with HP Labs and Purdue University for imaging algorithms. And uh, and so I did have a lot of focus in imaging. That was that core background of mine. Always loved, of course, science, nature, astronomy, and computers in general. But outside of work, for many years, I didn't do much technology outside of work. It really scratched my itch. So I'm more of a generalist, kind of into windsurfing, mountain climbing. I do a lot of backcountry with my daughter, climbing. We carry our snowboards up to the top of the mountain and then snowboard down. That's kind of fun. Fishing, scuba diving, that kind of stuff. So I've been kind of more of an outdoorsy person when I wasn't at HP. But when I retired from HP, I basically wanted a technical hobby requirement, something to kind of keep my technical brain going. And astronomy, I knew was at least going to be part of it, but I wasn't sure, everything I wanted to do. I did have some background in astronomy. As a family, we owned a little Tasco refractor, like a lot of families do, looking up at the planets and the moon. It was on a little equatorial manual mount. I never, as a kid, really knew how to, work it properly. Why does this work so weird? But anyway, as an adult, I bought a used Meade Schmidt cast screen, just a small one. You can set up out on the deck and you can look at the planets, the moon, just something very simple. And I had a film camera. I would take pictures of the comets, a couple of Milky Way shots, and so forth. That's, I guess, Hale Bop. I did Hale Bop and Hockey Talkie when they came by in the late 90s. But I did want a technical hobby when I retired. Uh, I was thinking about astrophotography, but I wasn't sure how and where to do it. I live in where there's a lot of clouds and rain in the Pacific Northwest. It's known for a lot of rain. We have a lot of trees. There's trees growing around the yard. I can see up in the sky, but low to the southeast and west, there's a lot of trees. We get east winds in the fall, and that really disrupts seeing and just being able to have a scope, set up. And the last few years, we've been getting a lot of fire smoke. We'll have like fire smoke for weeks on end in the late summer, early fall, which is normally our dry and clear weather. You can see some smoke on the right there in the sky, and then that's our back deck where it's really smoky. That's just smoke, and you'll have that for days on end sometimes. So no chance of doing astrophotography when you're doing that. But what I decided to get was I got a go-to Dobsonian. And the reason was I had such positive experience viewing planets and the moon and so forth from my deck that I knew a Dob would be a very good scope for that. I got a Go 2 because it's kind of nice to have it tracking when are looking at a planet. Plus, when I have friends and family over, you can do that. And I occasionally visit dark skies because I have some relatives. It's a couple brothers that live at very dark skies, and I'd bring it there. We could all do some family viewing. I had a little red dolly, and I dollied about, to move it out of the garage. So that worked out pretty well. And I was doing a lot of viewing with that. So how do I get from astronomy to astrophotography? So I saw some decent pictures of planets on cloudy nights, people using Go 2 Dobsonians, because you use high frame rates for planetary, so it doesn't matter that it only tracks crudely. So I bought a planetary camera, the ASI 45MC. I dug out my daughter's old laptop from college she had, and I learned how to use the fire capture, auto stacker, and Registax. And I went out there, started taking little pictures, and I got some initial success. My very first Jupiter, and my very first Jupiter with a couple of moons, my first Saturn, my Venus. I got Uranus, and so to me this was pretty exciting. Not really having any expectations of what this scope could do, being able to kind of just dolly it out, set it up, and you only have to film a planet for about 3 to 5 minutes to get a picture of it. So it was pretty fast and instantaneous feedback. So that was kind of fun. And then you can do Jupiter kind of animated, if you could, because it spins so fast over 45 minutes, you can kind of animate the frames, and that's also kind of cool. And then I brought into the moon. Lunar shots obviously are pretty simple. I built a little solar filter for the front of the telescope that restricted the aperture down to about 4 inches. And then and then had a solar filter in there that cut like 99.99% of the light. And then you can take pictures of sunspots. And with the solar cycle increasing, there was a lot more sunspots. So that was fun too. So all this stuff is not a stretch for a telescope like that, because you're taking a lot of fast exposures, and a lot of people with Go 2, any type of Go 2 telescope, Go 2 Schmidt-Cassegrains, Go 2 Dobsonians can do planetary and lunar and so forth. But then I started to point it at some deep sky targets, because it was like in May, there was no planets up. I was kind of bored. What do I do, And I wrote out on cloudy nights, hey, I was thinking about trying to do some deep sky object with my little planetary camera. And they're basically going, no, you can't do it. I'm sorry, you need long exposures. But someone said, just go point to a target you can find like M51, use short exposures, whatever your Dobsonian can support as far as exposure time. It's going to track good enough for something, and do that. So I did it for 6 to 8 second exposures, and I got a bunch of, targets, This was just with the planetary camera. I didn't spend that long on each target, 15 minutes to maybe an hour. And for me, this was pretty exciting because I didn't have any expectations of capturing deep sky objects. And just to be able to go out there and just do it, with a little planetary camera was pretty cool. So that really made me think, well, wait a minute, if I could do this with a planetary camera, what if I got a larger camera and a reducer? So I got the Nexus reducer, I got a APS-C camera, I got the ASI 2600 MC, and I got a dual narrowband filter. And as I kept on adding these things, it just kept on working. It wasn't a big deal. I found ways to stack all the short exposures with serial, do it quickly. So it wasn't that big of a time sink. And so, yeah, so I stayed with the short exposures with this scope. I utilized this one scope for everything: observation, planetary, solar, lunar, and deep sky. And here's the kind of examples of pictures I can get with it. So for me, this was satisfying. It's kind of a jack of all trades scope. It does a little bit of everything. It's not perfect for any one thing, but for me, just to be able to dolly this out on the deck and plop it down on a piece of plywood and then just kind of do a 2-star alignment and then start taking pictures and be able to get stuff like this from my Bortle 6/Bortle 7 skies. For me, that was kind of exciting. And so that's kind of stuck with it. I haven't gotten an equatorial rig. One problem with my yard is there's no really one place to set up, and I just kind of stuck with doing it with the Dobsonian, and I kind of got used to doing it that way, and so it works for me. So I'm kind of an odd duck with respect to astrophotography, at least for deep sky. For planetary, that's a normal type of scope for that, but for deep sky, it's definitely not used that much. But I did do a presentation on the Astro Imaging channel on it. There are several dozen people that I reach out to, and they've been doing it too. They're successful. A few of them have moved on to equatorial rigs. Couple have got C stars in addition. Most of them have done, had stick with Dobsonian. It works for them. They're happy. But but it is kind of a niche, type of astrophotography. And then, like I mentioned, I've been joined the RCA club, and what I teach is I focus on teaching the beginners. We have three people, and I focus on kind of a lot of theory and practice of astrophotography around collecting light, optics, the filters, the effectiveness, and so forth. We have another person that's an equatorial mount expert, and so he really teaches people on how to set up equatorial mounts, choosing equipment, and so forth. So we have, and then another person is really a hands-on at the deep sky locations, helping people when they come out there. So we've kind of split the task of how we help beginners. Um, so I'm kind of the lecture guy. And so this scope's a big fat sea star. Like Dan mentioned that I did do a 1 hour presentation on the Astro Imaging channel. So if you search for it, you'll see it. That's the icon for it, Deep Sky Imaging with the Dobsonian. And it was fun presentation to do. So now on to deep sky filters. So okay, deep sky filter. Three basic categories we're going to talk about. Okay, obviously, if you have a mono camera, you've got your basic LRGB filters and the narrowband equivalents. So this enables color imaging with mono cameras essentially. Then we have the narrowband filters, which for capturing the emission nebula. Okay, cutting out all the light pollution, but just focusing on the targeting one or two specific emission nebula. Then we've got light pollution filters, and they're kind of the opposite. They're like only cut out certain light frequencies. So the opposite, they like let everything in, but we want to cut, mercury and sodium vapor lighting. And they're essentially more for broadband targets. You can use them for anything, but the value proposition for those is that you can use them for anything. And so we'll talk about that too. So I'm going to move. I have a couple of icons that are over everything I'm talking. So I'm going to move them just for a second here. Where do I want the the screen blockers? Okay, here we go. So deep sky filters, the narrowband and light pollution filters. So why do we have those? Obviously, the primary purpose is to capture all of the good light, let all the good light in, but block all of the bad light. All right. And the more effective the more of the good light they let in, the more of the bad light they block, then the more effective that filter is. And we'll talk about that, the bandwidth of and the bandpass of the narrowest filters and why you want that and how to think about those filters. But also this a very important factor for light pollution filters because it's a trickier thing for a light pollution filter to cut out the light. So we'll talk about that. The second purpose of narrowband filters, though, is for mono cameras, at least, is for color reassignment. And we all know people do and capture hydrogen, sulfur, and oxygen, and then they reprocess it into a different color palette. So you can do any kind of arbitrary color reassignment that you want. So people will use these narrowband filters not just for light pollution, but really to isolate the gases and to assign colors to them and use them for artistic purposes, or for exposing structures slightly differently in a target. The Hubble originally used them for scientific purposes, but I think it caught on with the astrophotography public that it was a nice way to render our targets. A third reason, though, is you can do target dependent integration time. So if you have hydrogen alpha, oxygen, sulfur, some targets only have one or two of those gases. And so you can optimize by just shooting that. And an example here where you may want to shoot a lot more of one particular wavelength. So for the Squid Nebula, the hydrogen alpha in the background is reasonably bright, but the Squid is notoriously dim. And so people often capture 3 or 4 times as much oxygen as hydrogen alpha in order to kind of bring that Squid out. And that's an example where when you have independent narrowband filters on a mono camera, you can really optimize the capture of all the colors, whether it's luminance, the RGB broadband, or the 3 narrowband. You can optimize each target, and you can be more productive in that way. And so that's really kind of an important optimization for mono users. And then let's just do a quick RGB overview. Think about the human eye versus these filters and cameras. So the human eye has 2 types of sensors. One is called the rod. That's our monovision. It has a very high light sensitivity. It dominates when the vision is dim. That's why when things are really dim out, you only see monochromatic light. Things don't have much color. And our eye is dominated by rods. There's 100 million rod cells. But it also has these cones, which are the color cells. We have three colors, blue, green, and red. They're lower light sensitivity. They dominate in the fovea, in the center of our eye. So when it's bright out and you're really looking at something, you're usually looking at that with your color cones when it's bright out. There's only 6 million of them, so just a fraction of our light sensors are the color sensors, but they are concentrated in the middle, and our periphery is dominated by the monovision. And so, when you're looking at something and it's bright, then it's going to be your cone vision. And you can see the RGB there. You can see that the green and the red overlap pretty heavily. They're not, evenly spaced. But our brain does its job to sort out the colors to create the entire spectrum from the differentials between these different signals. So our color sensors have a lot of overlap, but a lot of RGB filters for astrophotography don't. They often have sharp cutoff, and I'll talk about ones that do and don't have overlap and what difference that makes. But that's one difference between our color sensors and astrophotography. Astrophotography has these sharp cutoffs, and like one frequency of light will fall entirely on one sensor or another in another color. Whereas with our human vision, it's more of this kind of smooth transition. So human sensors don't have sharp cutoffs. Color sensors for daytime photography don't have sharp cutoffs. And one reason, well, it's the design, is the technology used, but also it's a little closer to human vision to not have this sharp trade-off. And I'll tell you kind of why. But it generates a more natural image. And daytime photography is all about the best color representation, where astrophotography is less so. That's more about capturing the data, and you can assign colors as you please or tweak the colors as you desire. And so it's not quite as sensitive. But there are RGB filters that have the sharp cutoffs as I talked about, but there's also RGB filters for astrophotography that don't. They have the overlap a lot like color cameras and a lot like our human visual system. Most people use the ones at the top there with the sharp cutoffs, and I'll explain why. You can use filters that have more of a natural, transition between the colors if you show desire. So why do some filters match the human visual system better? And the reason is that in daytime photography, you run in situations where it's important. Here's an example where it's important. If you look at a rainbow, okay, out in the sky, there's a rainbow, and you'll see this nice rainbow from blue to red. If you capture that with a set of filters that have good overlap, you'll get all the colors. But if you capture that with a set of filters with sharp trade-offs, that's what it looks like. Because a rainbow, each band in the rainbow is one wavelength of light, it's going to trigger on the bottom example either the red or the green or the blue, but it's not going to have the smooth transition. It's just going to be a sharp cutoff. So if you had these kind of filters in your land camera, there would be situations where the colors just didn't seem right. They had these sharp transitions, unnatural transitions, and so forth. For astrophotography, it's not as important. So you tend to go with the filters on the bottom. And the filters on the bottom have one of the advantages. They have a gap between green and red, and that is the strongest line for orange sodium vapor lighting. And so when there was a lot of sodium vapor light in street lights and so forth, and the strongest single emission was around that frequency, they created a small gap there. So it's kind of a light pollution suppression kind of built in, just based on that gap. And also there was an overlap between green and red. And why was there? Well, that's where O3 is. And so this allows kind of a double capture. When you capture an equal amount of time of red, green, and blue, both green and blue will capture O3, which is a nice advantage. And so they designed these specifically to kind of avoid a little bit of light pollution and give you a little bit more O3 just by the design of where they cut off. So that's why they're designed the way they are. Also, I can't see the text chat, and if there's any text chat or any questions, chime in anytime. So just letting you know. Not rude at all, just to say, hey, Steve, what about this? So like I said, the ones at the bottom are the most common for astrophotography. And then let's take a little bit about O3 and the filter cutoff and overlap. Okay. So I've seen examples from people where they had the different types of filters and they said, here's kind of how they render differently. So if you have a lot of, if if you have a sharp or no, well, let's see, I'm trying to think. Okay, yeah. If you have a lot of overlap, then O3 is captured by both the blue and the green, and you'll get this aqua or teal kind of color for something like this, which is the crystal ball nebula, for instance. Okay. If you have sharp cutoffs, though, quite often the O3 only and they don't overlap. Then the O3 will only get green. Like in this case, these set of filters had no overlap between O and green and green and blue, and so only the green captured it. And then here's done with a color, one-shot color camera, which has a lot of overlap between the two. And once again, you're back to the teal. Now, obviously, in your processing, you can change the color of this anything you want. Once you put it in PixInsight or Photoshop. The point is that there is a little bit of a difference in these filters in the natural representation of the light when you first stretch it, before you start really tweaking on the colors. So it does generate a bit of a difference. So narrowband filters cut all the light except a set of very specific wavelengths, as we mentioned. You can get the single color bands for mono cameras. You can use a multi-band for mono cameras too, but most people use a single band. And then the multi-band, generally for color cameras, anywhere from 2 to 4 bands. The two obviously are oxygen and hydrogen alpha, which are the two dominant wavelengths in most nebula, but there's also sulfur and there's hydrogen beta. There is one filter called the Triad Ultra transmission filter, which on the right there, and it actually is a 4-band narrowband filter, and it captures the 4 dominant, because it adds hydrogen beta and sulfur to that. So you can get ones with up to 4. You can get ones with oxygen and sulfur, so with different mixtures and for different purposes. Some people do that so they can create kind of the Hubble palette with a one-shot color camera by using 2 filters. Some people also use these filters on the right as a luminance, a real narrowband luminance filter for a mono camera. So you capture all of the narrowband at the same time, but you cut all the light pollution. So that's also one function of these multi-band filters. Again, they're designed for narrowband targets, but this is kind of where the new section is. What is broadband versus narrowband, right? Narrowband targets emit narrowband light. So what is narrowband light? It's the light of a particular wavelength. And when molecules or atoms get highly energized, they glow. So it's not reflected light from the sun. It's atoms that are actually generating light themselves. And they glow at a very particular color, usually 1 or 2 wavelengths. Down to earth examples include the neon signs. They use neon traditionally, but also krypton, argon, helium, and mercury mixed together to make the different colors in those signs. Obviously, the older street lights using mercury and sodium have a lot of strong narrowband wavelengths. And then aurora, oxygen, nitrogen create strong. In fact, they can disrupt astrophotography. I've had it disrupted with aurora before, where I'm not seeing any stars. What's going on? The sky's really bright. I look up, oh, it's the aurora, Not so down to earth examples, of course, are all these emission nebula that we're capturing. Mainly hydrogen, oxygen, sulfur, and actually a fair amount of nitrogen, which gets swept up with hydrogen alpha because it's almost the same wavelength. So a little bit more on narrowband targets. So here's a spectrum of the Ring Nebula. And what it shows you is that it's dominated by H alpha and there's nitrogen in there too. So each one of these little circles is kind of a replication of the ring, but at each different frequency. So it's very strong ring there at H alpha and there's nitrogen. And you got a strong ring at O3, oxygen 3. But then you have like oxygen 1, you've got oxygen 3 is split in 2, there's oxygen 3A and B, and there's a weaker one at B at 495.9 nanometers. Then you have H beta there. H beta is usually about 30% the strength of H alpha. But look at these, we've got some tertiary emissions, helium 3, H gamma, H delta, we got nitrogen 2, helium. So there are, in some, especially planetary nebula, there are small emissions that occur on different lines. In fact, there's a few planetary nebula that has a fairly strong argon line. And so just to let you know that if you're capturing only H alpha and O3 of planetary nebula, on some of them you will be missing secondary emissions, and some of the secondary emissions are fairly strong. So yeah, there's H alpha and N2, O3A and B, H beta, O1, and then all the other ones that's talking about. Oh, and what's missing here is there's either no S2, no sulfur in the Ring Nebula, or it got clipped here. I think there is actually none. I think this target doesn't have any sulfur or a strong sulfur signal. And then what's my best approximation of the average of all large emission nebula of the wavelengths that come out? So from the best investigation I do, this is kind of approximately correct. The relative strength of the emissions. The strongest one is H alpha. If I say that's 100%, I have 100% strength, how do the other ones relate to that? Well, oxygen 3B is about 32%. It's about a third as strong on average as H alpha. And then sulfur is about a fifth as strong as H alpha on average. Now, there's some emission nebula that have strong sulfur, and there's some that have none. But if you just take 50 emission nebula and kind of average them together, this is what you're going to see. There's a little bit of argon. That's kind of in the infrared. There's N2, and that's pretty strong at 25%. But look at its wavelength. It's very close to H alpha. Most H alpha filters sweep up N2 if they're not too narrow. If they're 7 nanometers or wider, they typically get swept up in with the H alpha filter. And then you got O3B, you got O3A and O3B. Oxygen's a doublet. So one's at 495, one's at 500. O3B is about a third the strength of O3A. So a lot of real narrow filters get only O3B, but ones that are a little bit wider will also get O3A. And one consideration is if you're in very dark skies and you're thinking I'm a narrowband filter, you might consider a filter that's a little bit wider and just casts a little wider net and sweeps up some of these nearby emissions. Make sure you get N2 along with H alpha. Make sure you get O3A and B together, because it might be more valuable to get that extra signal than it is to toss out a little bit more light pollution if you're already starting from a very dark sky. So it's something to consider. So what isn't narrowband? What is what broadband? So incandescent lights, of course, fluorescent lights, LED lights, car headlights, the moon, just general starlight, you know, shining on the ground or shining on the up in the atmosphere, and then our sun, of course, if it's late in the summer and it may be 10:30 at night, but there's that little bit of sun still below the horizon on the northeastern horizon, northwestern horizon. Some examples, deep sky examples would be any star cluster. There's a lot of reflection nebula, like I think this is and this is the Embryo Nebula, I believe. We got the Ghost Nebula there, which is the reflection nebula, just dust. And then galaxies are primarily broadband. Obviously, there's galaxies all have a little bit of narrowband. Some have a fair amount, but they're dominated by broadband. And this one is the Sombrero Galaxy, and it's pretty much essentially a broadband target. So what in space isn't narrowband? So we talked about the narrowband targets. Here's the broadband targets. We talked about star clusters, galaxies, reflection nebula, dark dusty regions. We've also got mixed targets. There are some targets out there that are a healthy mix. I accidentally shot the Cocoon Nebula, the Trifid Nebula, I'm sorry, up there at the top with narrowband, thinking that both the red and the blue were narrowband emissions. It turns out that the blue is reflection. And you really want to capture that target with a broadband. And so I went back, captured broadband, even in my light polluted skies, even though it was low on the horizon near Portland City Lights, and I got a lot better image because it got that reflection nebula. And these other ones down here, like the Cigar Galaxy, obviously largely broadband, but people shoot narrowband H alpha to get that that's explosive H alpha coming out of the poles. And then both the Orion Nebula and the Horsehead Nebula area, they have a mixture. They're largely narrowband, but this Running Man Nebula is broadband. There's a lot of dust in both of these images that be captured with broadband. So, it depends on your imaging situation. If you're in really light blue skies, you just kind of punt and do narrowband captures and live with it. But if you can, you capture them in broadband to get those additional broadband features. So, okay, so the question is, okay, obviously, largely narrowband, you use narrowband filters. Healthy mix, narrowband filters situationally. You use narrowband filters if you have to, but it's kind of nice to capture in broadband if you can. And then this is the question. You use no narrowband filters on these targets, but do you use light pollution filters? And that's what we'll get to. So light pollution filter for broadband targets. What are they and how do they work? So, and I apologize for the depth of this next section, but as Carl Sagan said, extraordinary claims require extraordinary evidence. And there's a lot of people that have used light pollution filters, and I'm going to say that they basically, there's no evidence that they really provide value for broadband targets. And that's an extraordinary claim to some because, they've been advertised to people for, 2 decades and people use them and so forth. So let's get into that. So what's the premise of a light pollution filter? It's that much of our light pollution is from narrowband sodium and mercury vapor lighting. That's the premise. And that lighting is narrowband. So there's an opportunity to filter out only those narrow bands of light, but let in rest of the light through. So you let most of the light through and you just cut out the real bad light that's in narrow bands. So the loss of good light, which is typically 40 to 50% in these filters, is more than made up for by cutting out most of the man-made narrowband light. If it is true that artificial lighting is dominated by a few narrow wavelengths, then a light pollution filter may be better for all targets, including broadband targets. Okay, so here's an example. Here's the Optilong L Quad Enhanced filter, a very popular light pollution filter. There's where it lets the light in over a fairly broad range. I think it's about 55% of the light or 50% of the light. And there's where it filters out the light. And you can see it filters out along these artificial narrow lighting areas. And then it also lets in the all-important emission wavelengths. Even though we're talking about broadband targets, you certainly want to be cutting emissions from them. So they let those through. That's important. So why is a light pollution filter hard to do? And there's two reasons. It's hard. It's just fundamentally a difficult engineering challenge. And why is that? That's because all filters cut a fair bit of good signal in order to cut the light pollution. You saw that last one. It actually, if you average all out, I think it cuts like 45% of the light. But saving one photon of signal, right? In other words, letting that photon of signal through is worth more than cutting one photon of light pollution. In other words, if I cut one photon of signal and I cut one photon of light pollution, that's a loss. That's not even, okay? And it's because signal to noise is linear. The signal is linear in signal noise equation, but the loss of noise is a square root of the light pollution. So what that means is that for every one single photon I lose from the signal, I need to cut more than 3 light pollution photons in order for it to be advantage. Because the noise from light pollution is you square root it, and you don't with signal. You take it all. And so that formula of signal noise ratio is kind of is not advantageous for trying to create a light pollution filter. The other reason it's tough is that sodium and mercury vapor lights aren't really that narrowband. We've been told they're narrowband lights, we just don't think about it, right? We just kind of accept that. But you've kind of been misled about the lighting. And I'll talk to you about those lighting. But it makes it impossible to cut 3 light pollution photons without losing more than one target photon because they aren't that broad. They are actually fairly broadband lights. So here's the actual spectrum of these pre-LED street lights that we call narrowband lights. There's high pressure sodium on the top and mercury vapor on the bottom. That's just a rough diagram. Here's an actual spectrum of the high pressure sodium. It has some peaks, there's no doubt. There's a strong peak there in the yellow. There's a strong peak there in the teal, and there's a couple strong peaks in the blue. But look at that. It's fairly broadband. It spreads the light. It's because it's got a heating element in it. It's got some additional metals in there, and they emit light at different wavelengths also, just from impurities and from the mechanism itself that actually generates the energy, even though the sodium itself emits at primarily 1 or 2 wavelengths. It just generates a lot of other light. Mercury vapor is the same thing, and then metal halide is even more broadband in the sense it has a lot of different peaks at different areas. And when you look at them all in total, you can see incandescent. You can see it's truly a broadband light. Look at incandescent. But look at metal halide. Look at all these peaks. Some of those peaks are stronger than others. I agree. But man, they're all over the place. Fluorescence is fairly broadband. But then there's mercury vapor and high pressure sodium. And mercury vapor definitely has 4 or 5 strong peaks, but there's slightly different areas than metal halide and high pressure sodium. The one light that has really one strong peak at one spot is low pressure sodium. The problem is low pressure sodium is rarely used. Street lighting is high pressure sodium. There's only one place in the country that uses a fair amount of, or did, was Flagstaff, Arizona, explicitly for astrophotography purposes. They had an ordinance for using low pressure sodium, and they actually switched to an LED that has a single wavelength, and that is explicitly for astrophotography. If the rest of the world did that, then light pollution filters would have an easier time. But unfortunately, most of the world has these mixtures of metal halide, mercury vapor, high pressure sodium, some fluorescent, and a little bit of incandescent. And when you mix those all together, you get a pretty broad spectrum. And then finally, we add an LED, which is fairly broad, has a blue peak there, but it's also fairly broad. So here's two real cities today. Here's the spectrum of San Jose in 2023. Unfortunately, the guy who did this did it when there was an aurora going. He didn't know it at the time. And these two peaks I point at red are actually aurora. So for non-aurora purposes, just ignore those. But you've got a very strong blue peak for LED, and then you've got some secondary peaks here. Let's see, that are, yeah, the blue ED hump for the LED's primary phosphor is a blue, and then it uses additional phosphors to kind of redistribute that light into different colors. Then you've got the remaining sodium and mercury vapor lighting that does have peaks, but you can see there's these fairly broadband. I mean, there's over, if you integrate under this area, there's light across a lot of the spectrum. Here is Dallas in 2001 and 2003, and also a very similar profile. The scale's a little different, but you can see it's similar profile. You've got a few peaks there. The aurora was not going on at this time, so you don't have the aurora peaks, but you do have the sodium mercury vapor peaks, and then you've got the LED. And so the mixture of all the lighting types in use creates a fairly broadband light pollution. That's the problem, is that it's not just one type of light, it's a whole bunch of types of lights. And even the different sodium mercury vapors, they vary a little bit. So there's just too much variance. And then here's just recently the campus at University of Texas in Austin. So you can see it's also very similar. These all have very similar profiles. Doesn't matter where you go. A modern city kind of looks like this. So let's do it. First off, you have to translate these from light intensity, which is energy, into photons. So if you're going to capture this energy, I'll go back into a digital camera. It will translate slightly differently because blue light, each photon has a lot of energy. So as high as that blue hump is, it doesn't represent quite as many photons as you might think. And the red on the right actually represents somewhat more photons than you think, because they're just kind of wimpy, slow, low energy photons. They're lazy photons. So when you take the San Jose light, and which is the spectrum in units of energy is white, when I translate it back into units of ADUs, which is digital counts in your camera, it's the green line. Not a big difference. I just wanted to point that out, that you do need to make these translations to do everything correct. So I took all the light spectrums and translated them into digital ADUs that your camera would capture when you put these through a camera. So just if you're ever going to do your own models or anything, just kind of be aware of translating energy into photons. Okay, so I'm going to get back here. Okay, I'm going to skip that. Okay. Oh, I know. Some people are probably looking at that blue hump, thinking that, wow, that's the LED hump. What if we just filter that out? The problem is that even the LED blue hump may not last. So there's a general trend towards warmer color lighting. When LEDs first came out, they're generally very cool white lights. People are liking the warmer lighting, and the warmer lighting on the left side, like 2700K, 3000K, they have a lot more of their energy in the red, and that blue hump goes away. And so high traffic roads usually are 4000 to 5000K color temperature, but outdoor parks and residential are warmer. Most consumer lighting is warmer, and most wildlife friendly lighting is warmer still. And then also the color quality of the lighting is getting better. So if you get even 5600K, you get a high color rendering light, like a light used in a grocery store or any type of store where they want to sell you products. They want a high quality light, and that has a much broader spectrum, and that doesn't have that blue hump. The blue hump is for very inexpensive lighting. So anyway, that blue hump's going away, and then there's various organizations that are championing warmer lighting. The Dark Sky Association, right? For astronomy and astrophotography, says there's 5 principles. You know, all light should have a clear purpose. You should shield them, and warmer color light should be used where possible. Lights have to be 3000K, pretty warm. They can't be any higher than that, or they're not eligible for dark sky approved illumination. So they want warm lighting. So they want white lighting like that. It's better on your eyes. Doesn't blind you as much. Your eyes are more dark sensitive and so forth. The Audubon Society says blue lighting has been damaging for animals that do migration and for insects. National Sleep Foundation says that blue lighting is damaging to your sleep, and that also the National Library of Medicine, the Harvard Medical School has done a study, and they found that the blue lighting messes up your melatonin suppression, which is what you need when you're about to go to bed, and that you really want a warmer light. And they suggest staying away from cool LEDs. So there's a lot of people just saying, those warm lights that were really cheap, those warm LEDs, I mean, those cool LEDs, stay away from those. So there's going to be a trend away from those. So even that blue hump's going to go away. So what does the testing find on light pollutions find? So the only testing that had any level of robustness that I've seen where they do a direct analysis with and without the filters, and they also model the results to say, what should I expect? This is what we saw. This gentleman in San Jose did a very robust set of testing. He measured the light spectrum of his city. He measured the passage spectrum of his filter, and he did a model. And he said, you know what? Based on this galaxy and these nebula, it's going to be a net loss. And then he went out and he put in a telescope and had a filter wheel switch between the two constantly. And so he got the same data with and without the filter. And he said, yep, by golly, shooting without the filter was better than shooting with the filter from my light polluted city. Freestar 8 on cloudy nights, who's quite technical, did also a study. He found a small loss in signal noise ratio in using a filter. And then Jim Thompson does a lot of filter analysis. You may see in some of his technical reports. He's in Bortle 9 skies in Toronto, very light polluted. His modeling and his testing showed on average there's a net loss in signal noise ratio when using the light pollution filters, and he's used quite a number. My modeling, I took a measure of the spectrum of two cities, San Jose and Houston. I tested 4 filters, Oblong L Quad Enhanced, the L Pro, the Antlia Tri-Band, and the Hoya Starscape. I used the quantum spectrum efficiency for the ISI 2600 MC and the mono version, the 2600 mm. So 2 popular cameras, 2 popular types of sensors. Same type of sensor in the 533 MC and the 6200 MC. Those are just different sizes. On a typical spectrum of 2 targets, a typical galaxy and a typical reflection nebula. The results. So I'm about to show you the results. 100%. Greater than 100% means the filter helps you. Less than 100% means it hurts you. And what it showed is that all the light pollution filters hurt your performance on both the galaxy and reflection nebula. This is the signal noise ratio of using the filter compared to using no filter. So it's typically, 80, 85%, to say, what does this mean to my imaging productivity? Well, you have to square this result. So if you get 85%, you have to square it, and you lost 38% of your imaging productivity. So it's something that he would have to carefully measure it, but it's material. It's not immaterial, and it definitely doesn't help. So all robust modeling and testing that I've seen and everything I've been able to conduct to date says there's no filter that improves imaging productivity from light polluted skies for broadband targets. And that LED hump is likely to decrease. There's really less opportunity in the future to try to target, some particular wavelength. The remaining argument for LP filters, this is the argument I hear from folks, and it's a hypothesis. It says, although a light pollution filter will lower your signal and noise ratio, it means it'll make your image more grainy. If gradients are sufficiently bad and you don't have effective tools for removing gradients, and you live in an area that gets especially bad gradients, then removing the gradients will damage your image. So even if a light pollution filter lowers your signal noise ratio, once gradients are removed, the overall quality may be better because it may be easier to remove the gradients when you use the light pollution filter. So the light pollution filter, although it damages the SNR, it's a little grainier. If your main issue is around gradients, then maybe it can be helpful. Now that's a hypothesis. It has been tested and so far. It'd be much more difficult to test, but I'm just letting you know that for a couple of people that still use filters, even when they see like a presentation I gave or the argument, they will say, yeah, I just like it because I don't have to deal with gradients as much. So I'm just throwing that out there. Now, the next question is everyone says, yeah, but they work on emission nebula, right? Yes, there's no doubt they do. Any filter that cuts out a certain amount of light, but still lets in the emission wavelengths will be helpful. So I actually modeled an emission nebula with those light pollution filters. So let's take a look on a emission nebula. And so I have to look at the average performance of average emission nebula. So I use this. I said, let's just take this bulk, this emission nebula. It's like the average of all of them, just for fun. And I took the filters and I estimated, and this is what I got. All of them were positive. That means they helped your signal noise ratio. 134%, 238%, 137%, and the imaging productivity went up 1.8x. The tri-band really good, 5.7x imaging productivity on emission nebula. That's huge. And the reason why the tri-band is so good is it's a very narrow filter. It actually only let through 15% of the light pollution. It cut 85% of light pollution, but it still let 93% of the emission through. It had what's called a very high selectivity. This is the ratio of the target photons passed to the light pollution photons passed. So it's 6 to 1. So that's really good. And this is the tri-band. And you can see it's kind of a narrow band filter, really. It's not just a light pollution. It's quite narrow. It does have this additional band at below 450. They did that so that your stars are still fairly reasonably colored. You're sampling a little bit in all three color zones, but it sweeps up so much of the narrowband emissions because it's a fairly broad filter that it has really good emission nebula light pass. And so it's a good filter for emission nebula, there's no doubt. And in fact, oops, let me see. The C star is very similar to that filter. The C star filter to the right I have is very similar. It doesn't have that third hump, but so if you have a C star or a dwarf, your performance on emission nebula is going to be very similar to what I'm showing here with this tri-band. You're going to get about 5x imaging productivity, which is important, right? But look what a 3 nanometer filter. I put an L ultimate in through this testing. So it got 350% higher SNR. The imaging productivity is 12x. 12. That means for every hour I shot with the filter, it was like shooting 12 hours without the filter with respect to signal noise ratio. And for anyone who's used an L ultimate filter from really light blue skies on a truly emission nebula, it's just the differences are just so dramatic. It's like cutting through butter with a hot knife. It only passes 2% of the light pollution. Yet it does cut a fair amount of the emissions there. Look at that. It only lets 50% of the emissions through because it's so narrow. It cuts the nitrogen, it cuts oxygen 3b, it cuts hydrogen beta, it cuts all those third emissions. So it does cut down the amount of emission light, but it's just so effective at cutting light pollution that your productivity is still very high. So light pollution summary for light pollution filters is for broadband targets, I recommend using no filter other than UV IR cut. And for emission targets in general, just get a narrow filter. Don't get a light pollution filter. I mean, you can call it a light pollution filter, but really get a narrowband filter. Get a very narrow one. The narrower, the better. As long as your telescope supports it. Even if they do trim out a little bit of the good light, the narrower better. Now that's if you're in light polluted skies. But if you're shooting from Bortle 4 or Bortle 3, it's going to be more of a judgment call on do you want to let in additional emissions with a slightly wider filter or not. That one I have not studied. That's an interesting question, actually, an open question in my mind, where that trade-off is. Does anyone here use a wider filter because they're in dark skies, or do they just only do broadband? Yeah. I know some of you guys have hosted telescopes. I imagine you're probably mono.
I'm visual, so I got different reasons.
Okay, well, yeah, visual. Yeah, you want that H beta because I can see it. Exactly. Okay. So I kind of want to pause here for the light discussion, light pollution filter discussion, because it is for a lot of people that's kind of new information. It's something that's a little different than they heard before. Um, any reactions or thoughts on that?
Oh, well, yeah. I mean, like I said, I'm visual. So I've been grinning throughout this whole presentation because you've been justifying my existence.
Okay, good. I'm finally so you had a problem with your parents, obviously.
Yeah. Yeah, I like that when those when those dual filters came, I had an opportunity to test one once and I'm like as I was watching, I was thinking as you're presenting this, I was thinking signal to noise ratio. Okay, from a digital perspective, I see how that works. And I think the signal to noise ratio, has got kind of a different, for lack of a better term, transfer function. because as visual, I'm looking for the most amount of photon. I'm not looking for the color. I'm just
Right.
looking to increase the contrast. So I could
Yes, you
take a
are. The
50%
human
hit.
brain works a little different than a camera because we can increase the contrast digitally with
Yes.
processing. We only care about signal noise ratio, and you care about different things when you're directly having the human brain doing the translating. So it could be a little different function. And also, I'll go back to this slide just for fun. This filter here that has hydrogen beta here on the triad ultra transmission,
Yeah.
focus on that blue peak there at like 400 and what is it, 90. You probably know what hydrogen beta is, probably 495 or 490 or something. And so it's only about as one third as strong as hydrogen alpha, but it turns out our eye is a lot more sensitive to hydrogen beta. And so if you have a light pollution filter that actually only lets hydrogen beta and oxygen through, those two, that can be a very good visual filter, I think. Now, you're a visual guy, so what filter do you use?
I've got a couple of them. Well, I don't have any of the newer ones because they're just kind of cost. They're expensive. But
Right.
I've used like the Lumicons. I've been pretty much.
Do they let through hydrogen beta? You know?
I have to go back and look at them. I got a
Okay.
spectrometer. I've characterized the number of these filters for the clubs and that, and I'd have to go
Yeah.
back and look at it.
Yeah.
Um, it's been a few years though,
Okay.
unfortunately.
But our
Trying
eye
to
is,
go
the hydrogen alpha, our eye is has very low sensitivity to that because it's kind of getting out in that deep red zone where we're not too sensitive, especially when it's dim.
But I had
And
never thought about the H beta because all
yeah.
our eyes are different.
Yeah.
Yeah.
So for
I,
astrophotography, we tend to skip it, but it's actually if you're a visual guy, that would make you cringe because
I gotta
that's really a very key wavelength for visual because our eye is very sensitive to that blue light.
I'm gonna look into that. I hope you guys got a filter I can borrow.
well,
Steve,
Grant, actually, I have a, a Teleview nebulizer 2, which is a narrow band that cuts off right at the edge of that beta, hydrogen beta and O3.
Okay.
So it lets both of those through and it cuts out about everything. It lets in about, they advertise 90 plus percentage of the O3 and the hydrogen beta. And I used
Perfect.
it
That's
and
exactly.
it did a pretty good job
Yep.
on like Lagoon and things
Yep.
like that.
That's
So
exactly what I was saying. You want to let those two through for a visual. Those are the ones
What,
we see.
what's that
Steve,
filter, Andy?
what's that?
What's that filter that you
Teleview.
Teleview?
I
Yeah.
think they call it like a nebulizer 2. It's their latest version of the narrowband that they have.
Oh, okay.
It's a little pricey, but you can get a $50, $100 off if you get it pre-owned at Quality
All right.
Nights and stuff.
Thanks.
But I do have a question about that C Star. This discussion came up at one of the meetings about what does the C Star filter really cut out? Is it a strictly, they call it a light pollution filter,
Yes.
but is it
It-
strictly a
It's a
light pollution
it,
filter or
it's a broad dual band dual narrow band filter. There were new you can buy filters about as broad as the C Star filter that were one was the IDAS NBZ filter, which is actually the first narrow band filter I bought. It was only slightly narrower than the C Star filter, and the dwarf filter is slightly narrower than the C Star filter. But it's a dual band filter. It's just a very inexpensive one. But it does let through, all the emission. It lets through oxygen uh, oxygen B. I think it lets in H beta. It lets in hydrogen alpha and nitrogen. It doesn't let in sulfur. I think it just barely trims off sulfur, which is really strange to me. They just missed it, I think, unless the chart I'm looking at was incorrect, but they kind of missed it by a few nanometers.
and the conclusion for that is for emission
Yeah, it is.
photography.
And it
Yeah.
will only when you run the C star and you point at targets in the broadband, it will disengage the light pollution filter typically. And when you go to something like the Rosette Nebula, it'll by deep because it has them categorized and it will turn on the light pollution filter. So it's using it definitely as an emission filter for emission nebula.
And it would hurt you if you would use it for like galaxies.
Yes, unless all you wanted to catch was the H alpha in the galaxy. Yeah.
Steve, George Gino here. A question about the light pollution that these filters are attempting to think. I'm in an area where, of course, there's the sky glow from St. Metropolitan St. Louis,
Hmm.
but there's also neighbors with these bright LED backyard lights and that sort of thing. Is the nature of the light pollution dealt with differently by these things? For example, in that case, where you get
Yeah,
the basic sky glow versus this radiant
yeah.
shot across the
What
yard.
you're saying is, what is my spectrum? First off, the spectrum of the light pollution will shift from zenith down to the horizon, and we're on the
Yeah,
horizon, obviously.
right.
And in Flagstaff, Arizona, when they did the analysis, they had to talk about evenings where the stadium lighting was on because high school sports was going, and nights where the stadium lighting was off because the spectrum was very different because the metal halide lights for stadium light was so bright. And Flagstaff is kind of a dark sky kind of city that it just dominated. And it's kind of like, well, it's stadium night. So you're kind of like that. It's like, the neighbor lights come on. It's like it's stadium night. So it totally changed the spectrum. You have a unique spectrum. And when their lights are on, it's going to be whatever their color spectrum of their LED light is. Are these lights kind of, warmish, or are they super bright
Oh
blue?
no, they're a bright blue. They're
Yeah, so
cold.
they're those classic 5600K, 5000K lights that people are saying, please don't use these anymore. They're terrible to use at night. And they have a big blue hump. Um, it's possible, in theory, you could have a filter crafted for you for that particular light that would cut out just the blue hump, but it might only cut out maybe
Wow.
10% or 20%. That may provide a benefit, but it would be very specific, and the benefit may still be modest, but it'd be possible. I put Flagstaff, Arizona's light spectrum through my model, and a couple of those filters provided a benefit because Flagstaff has such narrowband lighting by design that those filters do work. So it's not like it's impossible. It's not like it's impossible to design a light pollution filter if you have the right spectrum and you design the filter for that spectrum. So in theory, if you had a particular light pollution spectrum, you may be able to do something, but good luck. Yeah, unfortunately, yeah. You gotta,
But they're all good.
you gotta buy them some nachos and and some pizzas to their door, I think.
Yeah.
This has been a great discussion. I think this is the best filter presentation I've ever seen. So thanks for putting this together. One reason I have had, I think, success with light pollution filters with a one-shot color camera, even at a dark site, is natural sky glow itself. And as you pointed out about, the eye isn't really maybe sensitive to some of the longer
Mhm.
red wavelengths, but
Mhm.
cameras are. And I find I can take much longer exposure with a light pollution rejection filter, even if I'm at a dark sky site.
You can take longer exposures. Longer exposures, some people consider a longer exposure a figure of merit, salient feature. And some people consider longer exposures just a simple fact that you're collecting less light. For instance, they would argue, well, you could constrict the aperture of your telescope with a ring and cut down half the light, and you can also take a longer exposure. But that doesn't mean it's a positive attribute. So, but you're right, you can take a longer exposure
No,
and have
you're right. I'm using sloppy wording.
okay,
I should say that it's like you point out, the signal noise ratio or the contrast between
yeah,
the
no,
background
the
and the
contrast will be
wavelength I'm trying
higher.
to get at.
Yes, you know what's interesting in an image. Often the contrast will be somewhat higher with these light pollution filters. It'll be a little noisier, and it's hard to see noise. If you've ever stacked like all your lights, then stack 75% of the lights, you can almost can't see the difference. That's such a small difference. Stack half the lights, you can really see the difference. So a 10 or 20% reduction in noise or increase in noise, it's a subtle thing, but you can see a 10 or 20% increase in contrast. And so what happens is the natural
Hmm.
contrast image will be higher. You'll see it in your light. It looks better. It's a little easier. It's almost like someone took your other light and adjusted the contrast, even though it's a little noisier, and you will trigger on the contrast, and it may be more pleasing. Now, once you stack it and you actually adjust the contrast to wherever you want, you'll see the noise. So it's an interesting thing. I think there's a psychological factor about seeing contrast. Certainly visual, it's important because it's live. That's all you're going to get. You can't capture it and process. So if you have higher contrast, you may be able to detect an object where you couldn't. But in a light, you may have more contrast. But if the signal noise ratio isn't there, that's really the salient feature when it comes to actually finally processing an image. So But you're right. You may see higher contrast, which could have an immediate advantage. It could be important for EAA, for instance, where you're not processing the image and maybe you're not adjusting the sliders, but you just want it to be inherently higher contrast. Yeah. I do have a couple more things on narrowband filter. I just wanted a couple things. So I mentioned these secondary wavelengths. So here's wider filters we talked about can cut and sweep up more wavelengths. So here's the IDAS NB1. It is an emission nebula filter, but like the C-star filter, it is designed to capture a little bit more light. So if I was in like Bortle 1 skies and I still want to use light from Fuchsia, I'd be tempted to use something wider, compared to this Ultimate, which just doesn't even even cuts out some of the O3 because it's so narrow, right? And then some filters try to do both, right? They try to be very narrow and capture it all. So here's that Triad Ultra, and there's that H beta that people are talking about on O3 that are important for visual. Like this would make a good visual filter, because even though you might not see HA too much, at least it lets in H beta and O3, which are important visual. And who knows, if a target's bright enough in HA, maybe it might trigger a few cones. I don't know. So there's that. And another one is the general characteristics. So all else being equal, the narrower the better in general. But here's things to watch out for in filters. The peak transmission varies by brand and model. So some actually cut 15% of those emission nebula, and some only cut 4 or 5%, almost let it all through. So there are differences in the quality of these filters. Then your telescope F ratio. If you have a F4 or slower or F5 or slower scope, you can kind of buy any filter you want. You have something that's faster than F4, you got to really watch what filter you're buying, especially when you get really narrow, because it shifts the bandwidth of what the light that the filter filters. And I'll talk a little bit about that.
Yes,
and then, you mentioned, do you need longer exposure times, as many have claimed? So I'll talk about that. It's actually, do you benefit from longer exposure times is really the claim, I'd say. And we'll talk about that. And then are some of these secondary emissions, how important are they? So narrower is better. So here's a math example. I have a mono camera. I'm capturing H alpha emissions in a target in a light polluted sky. And for every 100 H alpha photons, I get 3,000 light pollution photons. So 30 times more light pollution than the signal. So very light polluted, okay? So then I get a filter, right? I have no filter. I get 100 HA photons, 3,000 light pollution photons. So the sig-noise ratio in that situation is 1.8. You take 100, which is a signal, divided by the square root of all the photons that come through, which is the 100 plus the 3,000. You do the math, 1.8. Now I put a 25 nanometer filter on there. It has 95% HA transmission, so it only cuts out 5% of the HA. So I get 95 HA photons, but it cuts out 95% of the sky photons, so I get only 250. So what does it look like? Well, the signal noise ratio is now 95 divided by the square root of all the photons, and that's 5.1. That's 2.8 times the signal noise ratio, and that's 8x better productivity with that filter. But now I get a 3 nanometer filter. The problem is its peak transmission is not as good. It actually cuts out 15% of the HA transmissions. That's not uncommon with a filter that narrow. It's hard to design it so that it lets in all the HA and be so narrow. So now I get 85 HA photons, but I only get 30 sky background photons. My signal noise ratio is now 7.9, 4.4 times better. My productivity with that filter is now 19 times better. So even though it cut out additional HA photons, which is bad, it just was so much better at cutting out the background that my signal noise ratio is better and it's much more productive. Now going from 25 to 3 nanometers isn't 8 times more productive. It's only a little more than 2 times. So there is this kind of diminishing return, okay? But that's how narrow filters are better, even if they do restrict the light, the good light a little bit. And then here's just examples of how the filters vary. This is from Jim Thompson, who does a lot of filter testing. So he measures the spectrum. Someone was online, I didn't get your name, but you're measuring spectrum of filters too. So it's common to do, but you can see they're quite varied. But here's more important. If you have a low F ratio scope, it will shift the band path of the filter to the left. It will actually let in shorter wavelength light and block the light that you might want. And so you can see with this middle, the HA, the native filter is centered around HA, but if you shift it all the way to F2, almost no HA will make it to this filter at F2. Now, a telescope that's f2, not the entire surface of the optical element operates at f2. It varies. So you can model it. You can say, look, the light comes in at a telescope at different angles. It's the center of the mirror and the center of the optics, it's at 0 degrees angle. But at the edge, it's at a certain angle. And so Jim Thompson actually, and Charles Bracken did too, they actually could model it and they basically average it. So here's like an f 2.9 scope, I think it was, or f2 point something, and f 2.8 reflector, and you can see that 16% of the light comes in at f 2.9, some comes in at f3, some comes in at f 5.6, and so the problem is the band shift of these filters is inconsistent. So you can't get a 3 nanometer filter for an f 2.8 scope that works over the entire surface of the mirror because it's shifted differently at different spots in your telescope. So quite often when you have very fast scopes, you just can't take advantage of really narrow filters effectively. You generally get a wider filter and you might get it pre-shifted, and it's generally a little wider. So I'm just letting you know that if you have really fast telescopes, the narrow filter situation gets complicated. Gets complicated.
Can I ask a quick question of the group? Is anybody using a scope that fast, faster than f3? I know that's a Lockwood kind of thing.
It's a Hyperstar.
A Hyperstar?
Yeah.
Hyperstars and also the
Origin,
Celestrons.
Celestron Origin, and any
They're 2.2.
yes, and then people have f4 Newtonians with the Arizona Nexus, and they're f3. My telescope is f3.7, so I had to worry about it.
Mine's f3.65. Yeah.
Yep. The good news for me is I was able to mount my filter in front of the reducer, so the filter operates at 4.9, and then it gets reduced to f3.7, so my filter operates at a very low f ratio, and I don't suffer this. So I was able to put a 3 nanometer onto my f3.7 scope.
I'm f7 to f12 anyway, but I was just f3 scopes, f2 scopes, man. Those are, light buckets, and it's just, I've never really
well, there's just a lot. Yeah, you have to have, there's a lot of things that need to go right to make those scopes work. And I'm letting you know that the filter discussion becomes complicated. Okay, so I'm going to skip some of that, but little advertisement for Jim Thompson. He kind of models basically all the different gases coming through the filters and at different F ratios, how many of them, what percentage of it gets cut. And you can buy pre-shifted filters. That's expensive. Quad band radiant triad ultra narrow filter. They do sell a pre-shifted one for $780. That's shifted for scopes for f3 and faster. Okay, so you can get them. They're kind of a specialty item. Yeah, they shift the bandwidth so that when it gets
$780.
That's it. Hey, we all have lots of money to spend, so here it is. Yeah. Okay, additional conversation. Do you need longer exposure times? Sometimes you do. It depends on several factors. For most people, the answer is no. If you are taking reasonably long exposures already, 2 to 5 minutes, it's generally no. But there are a few corner cases. There are exceptions, okay? So here I have 4 hypothetical people. Joe. There's Joe with the f2.2 Rasa. So maybe no one in your club has one, but he has one. Now, he's in Bortle 7, so he's in light blue skies. And he's using a full-frame camera, 2400 MC, which has big pixels. And he uses it in high gain mode. 140, so his camera read noise is pretty low. So here's his exposure time so that his camera read noise only adds 5% extra noise to his stack, which is considered a trivial amount. So if he's longer than these exposure times, he's great. With no filter, he only needs a 1/4 second exposure. Wow. L enhanced, he only needs 1.5 seconds. Even with the L ultimate, he'd have to get a pre-shifted one. He only needs 8-second exposures because his scope is so his light pollution is so high, his scope is so fast, and his pixels are so big. But let's take the opposite extreme. Barbara. She has an f7 refractor, so it's kind of slow. She's in Bortle 4. She lives out in the country. She lives in dark skies, but she's using a small pixel ASI 183 MC. It has very small pixels. And also it's an older camera that has higher read noise. Even at 100 gain, it's 2.4. For no filter, she needs a 550-second exposure. And with an L enhanced, she needs 3,000 seconds, and an L ultimate, she needs a 4.5-hour exposure for 5% read noise. I know these are extreme examples, but I'm letting you know this is why situation matters. You can't just say yes or no. Look at the difference here. So let's take more 2 reasonable in the middle. David has an f5 refractor, very common size. He has an ASI 533 MC with 3.76 micron pixels, very common pixel size, right? He runs it in high gain mode, 100. Very common also, 1.5 camera read noise. So NOR filter, he needs a 14-second exposure. For L enhance, he needs 70 seconds, and for L ultimate, he needs a 400-second exposure. If he was taking only 2-minute exposures, he would get some benefit taking longer exposures with the L ultimate. Susan, different situation, f4 Newtonian, Bortle 6, a little more light polluted, same camera, same setting, but because her camera, her light pollution is higher and her scope's a little faster, she's kind of in a better situation. With the L Ultimate, she only needs 120-second exposures. So if she has already taken 120-second exposures, she doesn't need to do anything. I'm just letting you know that it's very situation dependent on whether you benefit from longer exposures when you have a very narrow filter in there.
Question: are you talking a broadband target here or a narrowband?
It doesn't matter the target. This was related to the this is related to how much light pollution noise, how much the read noise of the camera is above the light pollution noise, because light pollution noise typically is the dominant noise factor and is the limiter to rendering subtle details that just barely rise above the background. So it's how much the read noise is above the light pollution noise. If you have a very bright target, that adds additional noise, and these exposure times can go down a little bit if you're shooting an especially bright target. So if you're unsure about exposure times, there are various tools online that help you estimate that. I have a spreadsheet that I use to calculate it. You input all sorts of parameters and so forth. And if you have an uncooled camera, it calculates the thermal noise. I'm not going to talk about it, but I just let you know the backup. I do have a spreadsheet, and you can do it. But basically, you just type in your camera, settings. You tap in your essential what your Bortle is, what the moon phase is the half moon, quarter moon, how far away is it from your target, and then it basically says, okay, well, here's with these list exposure times, this is how much your camera read noise is, and this is how much your camera thermal noise contributes to your noise stack. So you can calculate it. And I have a spreadsheet that does, and that's how I did those examples, just pumping it through the spreadsheet. And then one other last tidbit is a color camera narrowband challenge. So one issue with color cameras is getting a clean O3 blue separation. So here's a squid nebula I shot with my Dobsonian, and it was hard to get the blue squid to come out because there was a lot of H alpha in the background. And the problem is this: I'm using a one-shot color camera, and the blue is okay because you get the oxygen shows up in both the blue and the green channels, and the red channel doesn't pick up too much. It's way down there. But look at this. For the H alpha, which is stronger signal than the oxygen, the green picks it up fairly strong. The blue picks up a little bit, but the problem is H alpha in the squid nebula is like 10 times more intense or 5 times more intense. So you get a very strong H alpha signal in your blue and green channels. Okay, so the problem is the targets are very strong HA and weak O3. So here's an example. Here is the HA channel, the red channel out of my camera. Nice strong HA signal. Here's the squid, the blue and the green channel out of my, averaged out of my camera. You can see the squid in there a little bit, right? But look at the clouds of H alpha hovering around. They're suppressed, but they're not gone. That's a problem when I'm trying to bring that blue squid out. Here is the color camera with the H alpha subtracted. And it's using a basic formula. This is a crude simplified version, but basically you take the average of blue and green and you subtract a little bit of R. And you subtract the amount of R depending on the absorption of that camera on how much hydrogen alpha is absorbed in the blue and green channels. And in my camera, I have to subtract about a 15% or 0.15 times R, and it subtracts the H alpha. So look how much cleaner that squid is. I created a clean O3 channel with a color camera with my L Ultimate filter with a one-shot color camera by subtracting the residual H alpha that leaks into the red, the blue, and the green channels. And so that can be done.
That's done on a pixel by pixel basis.
Yes, you do it with pixel math. Yeah, both Cyril and PixInsight support pixel math to do this. Here's an example compared to an actual mono capture. The mono capture, so here's the OSC with dual narrowband with subtraction, and this is an actual mono capture. It was done with a slightly smaller aperture, so the resolution is a little lower, but you can see that they both don't have the HA signal in the background. So it does a pretty good job. So if you do have a one-shot color camera and you're shooting targets that have a weak O3 signal, there are ways to kind of reconstruct it if you want to better represent it. So anyway, and then finally about monoluminance. When shooting broadband targets with a mono camera, you have a choice, LRGB, how to best take advantage of luminance. There's a common technique to shoot one half the time with L and half the time split amongst R, G, and B, right? And then you mix these. For broadband targets, that increases the total number of photons you get by 2x. That's a good thing. There is a debate on cloudy nights on the gain in luminance SNR versus the loss in your chrominance, because you're actually trading off some color fidelity in doing that and how the human visual system interprets that. So that's just an ongoing debate in cloudy nights. There's people that say, no, it doesn't really help because blah, 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 and they have all these reasons. And they're technical people. And there's people saying, no, 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 it does help, and it's for these reasons. So there's the shoot all RGB camp versus the LRGB camp for mono users.
Let's
I
fill
don't have
in.
I don't have direct experience in this, so I don't have anything to add to this. Only that's a debate. I will, from my color imaging background, where we had a lot of imaging scientists and we did separate luminance from chrominance signals in color and in monitors and so forth. I will say that in my work evaluating human perception of print and display quality HP and using multiple levels of colorants to minimize noise, like we use different shades of black in our inks for our graphics printers, when we optimize these, it was clear that the human visual system is most sensitive to luminance in our recognition of details. I believe the human vision science would generally support. If I gave this argument to all the imaging scientists at Purdue University and at HP, they would say generally the L plus RGB productivity benefit hypothesis would probably be supported. They would generally say, yeah, L plus RGB is probably a good way to go, just from a fundamental imaging science. But I can't say from actual testing because I haven't done it. There's that debate. I don't know. Any LRGB shooters here?
Yes.
Do you do?
I still use a CCD camera where there's definite benefits to being able to bend the RGB.
Uh-huh.
And
Yeah,
so
because of noise.
yeah, so that's kind of where that comes from. But as
Yeah.
with my where with the newer CMOS cameras and things like that, where they don't really have true on pixel binning or on chip binning, I think the RGB is probably the most common, best way of doing it without luminance.
Yeah, it is simpler to process, that's for sure. I mean, you just less steps and less things you have to learn, for sure. But I'm
Andy,
just
it
letting you
looked
know
like
that, if you're talking about just noise and so forth, you're probably a little benefit to the LRGB, but boy, I tell you, it is, someone would ask the question really like cloudy nights, and there's an icon for you eating popcorn, like you're ready for the show. And I kind of put that up going, okay, I'm ready for the debate now. Here it comes. Anyway, I just want to throw that out there. I think that concludes everything. So,
Steve, I have a question for you.
yeah.
Hey, I image with a one-shot color camera, and it's been like a discussion online, like you said, where some people say if you're a one-shot color imager, there's no need for using a luminance filter. Lately, and in the past, I guess I've read two different arguments. I've read that some people say using a luminance filter on top of the uh, added luminance filter to your one-shot color provides a tighter cutoff and has the potential of reducing star bloat and chromatic issues at longer focal lengths, which I do. I image from with a Edge HD 8 and 9 1/4.
Yep, I cut my slide on that, but I had a slide on that. So what you're talking about is a luminous filter is generally a UV IR cut filter. So it generally lets in the wavelengths from approximately 400 to 700 nanometer. But there are different filters that are more restrictive. There's ones that actually start at like 420 nanometers and cut it out about 670. And there's ones that actually let 380 to 720, much wider, let some ultraviolet, some infrared through. And what's this about? Let's say you have a mono camera that's broad spectrum. It can go from 350 to 1,000 nanometers, right? Why do you decide how much to cut? And it often has to do with the quality of your optics. If you have a very inexpensive doublet refractor, it can't focus all the different wavelengths of light at the same time very well. And so as you get towards the very blue end of the spectrum, it becomes defocused and you get blue star halos. And so if someone has inexpensive optics, they'll often they can get a luminous filter for a one-shot color camera that is more restrictive, and it cuts out those fringes. You don't get the fringing. They lose a little bit of light, they lose 10% of the light, but they cut out that light that's not being focused. For someone who has very high quality optics, either a quadruplet or a reflector, which generally does not have that same focusing issue. It can generally focus all the frequencies of light, and they may opt for a filter with a little wider. So the other reason people on a one-shot color camera use a luminous filter is if you have a one-shot color camera that does not have a built-in UV or cut filter. So an ASI 2600 MC has the cut filter. I believe the MM does not, but certainly some of the planetary cameras do not. I don't have it memorized which do and don't, but there's cameras that have a built-in what they call the UVR cut window and on it, and there's ones where the window's just clear. It lets all the frequencies through. It depends on the camera. But if you have a camera that's a broad spectrum camera, you certainly should generally put some type of UVIR cut filter on there. And that can be called a luminance filter because that's generally what they do. Does that make
Hmm.
sense?
Yeah, it does.
I have to say that's been my experience too. I buy sometimes cheap old Nikkor lenses from the 1970s,
Mm-hmm.
and they're wonderful lenses in the visual, but at H alpha they just are not meant for that. And with the
Mm-hmm.
wider sensitivity of an electronic sensor, I get red and purple fringes and so
Yep.
on. And it's a wonderful lens with a standard camera, but when you put it on an Astro camera, it just is not up to the modern standards, as opposed to like a Stellar View apochromat doesn't show any of those effects. Hey,
Interesting.
one
Yeah.
question I have, when you mentioned the UVIR cut filters with 2600 ASI 2600 MC Pro. Um, I've heard different things online, and I kind of question my own experience. I was told that they put in a Bader UVIR cut on those, which is a great filter, but I still get a little bit of uh, IR past the H alpha line. So I'm suspicious it's not really or I should say longer wavelength than the HA. So I'm still suspicious it's not really a Bader filter. I was wondering if you
Hmm.
had any opinion on that.
I know nothing about I mean, I've seen I've seen the spectrum profile of the filter they put on it, and people have actually measured it, but also there was one spec that came out once. I don't know where they get the filter, where they source it, and I can't even remember exactly where they cut off. I think they cut off just below 400 nanometers, and they cut off just below 700, as I remember, but
Hmm.
still way above HA. HA is what,
Oh yeah,
654? So I think
yeah.
they
So they're
I
way
think they cut
out.
off at like
Okay.
390 or 395 and then 690 or something like that, if I remember correctly. But I don't remember exactly. So I can't answer that. Yeah.
Yeah, yeah, I have one more question.
Sure.
Do you have any insights on the IDAS dusk till dawn filter?
I have no idea. I'd have to look it up.
Okay. On paper, it seems to be an interesting filter. It's hydrogen alpha, oxygen 3 filter. I think at 7 to 9 nanometers, if I remember correctly. But it also passes light at the near infrared. Um, and it has some properties that reveals
Okay.
the ion data from comets.
Okay. I'm going to
I
share
believe
in just a
this is
second.
right.
I'm going to share here it is, just so we're talking about it. So I'm sharing
Yeah,
oof,
yeah,
there it is. Okay. So everyone see this?
yeah.
Yes.
Okay, so what this kind of filter is this is what's often called a galaxy filter. And what this is a filter that, first off, it lets in three bandwidths within the visual spectrum. You see a band pass there between 400, 450, 500, 550, 650 to 675, whatever. And those are, first off, they're capturing some of the emission over there. It's also, we have three for each of the RGB, so you get generally good star quality. So you generally get a good color balance. But then it lets in a lot of infrared. Why is that? Because light pollution is very weak in infrared, but galaxies are actually still fairly strong in infrared. And if you have a optical device that can capture infrared and focus it like a reflector, this is often called a galaxy filter. They call it a reflection nebula filter. May be true too. I'm less familiar about the infrared of reflection nebula, but that could very well be true. But certainly for galaxies. And what it is people who have extreme light pollution will sometimes use this for galaxies if they have a broad spectrum camera, right? A camera that goes deep into the infrared. They have a reflector, and they'll use this for capturing galaxies. And what they're doing is throwing away most of the light from the visual spectrum, but only enough to get good stars and to get the emissions in the galaxy, like the hydrogen emissions. And then they really focus on capturing the bulk of their broadband in the infrared. Now, infrared doesn't focus as well in general because it's just the longer wavelength. It's just a nature of optics that the sharpness of things is going to be inversely proportional to the wavelength. So it's going to be half as sharp as the visual spectrum or so forth. But if you're got a fairly large aperture telescope, that loss you're probably seeing limited anyway, and so that might not be a big deal. So it's a specialty filter. It can work. I've never tested it. I've seen videos of people test it. I've never seen them do super side-by-side technical analysis, but they're not real common, but there is some promise to these filters in particular situations. I would say very light blue skies, a reflector with a fairly large aperture, so you can still focus this light to get reasonable clarity, and it probably might be worth a try.
Yeah, interesting.
Yeah.
Thank you.
Yeah. Astrodon used to sell one of these filters, and they were made especially for a handful of galaxies, MiFi galaxies or something. And
Right.
I've also seen this use if you've heard of one of those forefront on access guiders, a lot of those use NIR or IR stuff for guiding because it cuts down the sizes of the stars.
Mm-hmm.
But they typically, for the guide cameras, they use full big cameras. They don't use little ASI 120s and things like that.
Okay. Yeah. I know Queeve the Lazy Geek in Tokyo tested one of these types of filters about 2 years ago.
Yeah,
And
he tested.
you could always look at his video
Mhm.
and he doesn't do necessarily a super sophisticated test, but at least it gives you some impressions of what it's like to use a filter like that.
Yeah, I think he tested the GNB
Okay.
version of this filter.
All right.
And then there's a guy called Cody something, Astro Cody, I think.
Mm-hmm.
And he specifically tested this one. I just can't remember which scope he
Okay.
paired it with. If it was a
It should be
Newtonian
a
or
reflector.
okay.
You should not. I don't
Interesting.
think you'd want to try one of these three. I don't refractor. Someone who's an expert in refractors could let me know, but I'm pretty sure that they're not designed to do deep infrared.
Okay.
That's why they have so many elements and they special glasses. They work hard enough just to do the visual spectrum well. It's like
Mhm.
they really had to work hard. And even if you have a reflector, if you have a reducer, coma corrector that has several glass elements, that could affect your ability to focus um, the long wavelength light too. I'm not sure. It gets kind of complicated when you're trying to do a very broad spectrum of light and focus that through optics. It gets harder. It's just a harder job to do. The broad, and
Yeah.
this is going from 400 to maybe 1,000. That's 2.5x wavelength size. That's giant. That's a giant range of wavelengths that you're capturing and trying to focus. So yeah, not every telescope's going to do that well.
So is the corrector on the front of a Schmidt tending to limit the IR transfer?
Good question. I don't know about it. I would assume that it has full spectrum. I know people do. I think they use SCTs for infrared planetary to capture methane on Jupiter. So I think they pass at least methane. I don't know what methane is. I think it's in the infrared, I believe.
Standard commercial SCTs or special built?
I think commercial SCTs. I think the glass
Oh,
does not
okay.
cut UV-IR on commercial SCTs. Yeah.
I kind of asked that for Miguel since he's using SCTs.
Oh, yeah. Someone else can answer that then.
Yeah.
Yeah, because glass can cut UV. I know that.
Sure.
Now, I know you wouldn't need for visual, you wouldn't need see the UV or the IR, but for visual, would have characteristics like you see in the middle of this spectrum Would that be good for a light polluted sky with a let's say just a typical Dob?
For visual?
Like yeah, something with that you're just filtering out in the 500 range and the 650 range. Would that be considered a light pollution filter for visual if you just had a filter that
I would
did that?
defer to, you have a couple visual guys on. One was just speaking earlier. I would defer to them with the experience. I've only used filters a couple times visually, just plain. I don't have a broad set experience. It's really kind of outside of my expertise using filters for visual, other than, the write-ups of filters and reading reviews, but not actually using them, you know. I did
Yeah, I've
use
always
one
found that
that
light
let
pollution
in
filter.
H alpha.
So,
Yeah, I did use one that let in H beta and O3, and it worked on planetary nebula, and that's the limit of my experience. Yeah.
mhm.
That was me talking about visual, Grant, up there. So when we were back there talking about that, you had a filter that had a high blue pass. What was that? What was that filter that you mentioned?
That had both H beta and O3.
Yeah,
Yeah, that was
you said
the
that might be
Radiant
good for
Triad. That was the Radiant Triad filter. Yes.
radiant.
Yeah, which is, it's not for visual use, but I was just pointing out that it would probably be, it's super expensive. It would probably be a good visual filter,
Yeah.
just
Well,
because of its nature.
yeah, and it's all about contrasted visual. I mean, when we're trying to get planetary nebulas, stuff like the emission nebula, that one you just head up the DTD,
Yeah.
I have to wonder because in my day, our filters were always narrow band, just O3, H alpha. They were not these multi-band filters, and they were great for things like the Ring Nebula. I mean, I got
This one on the right here, this Triad Ultra Emission. So those two bands there, that green and blue, are the O3 and the H beta. I think this is what you were referring to.
yeah, yeah,
Yep.
yeah, and that's great because I've got actually one of my better ones is like I don't remember what the numbers were, but it was tight on the O3.
Hmm.
And I'm telling you, I mean, when you looked at a emission nebula like the Ring, I mean, it was like white on black. It
Yep.
it pulled those things out no problem.
Yep.
Um, but the blue, I had not thought about that with these narrow bands. I always looked at the narrow bands as as I, there's something in me that says that those would be some good visual things
Oh
because
yeah.
they're going to allow the light through that you want and not the light that you don't want. And then you get this increase in contrast.
Yep, I think this Triad Ultra would be a good visual filter, to tell you the truth. And for
I,
what it's worth, it lets in HA and S2. I know that those are hard to see, but having
I
pass through might be beneficial. I don't
Any
know.
photon hitting a cone or a rod is good.
Exactly. So it'd be interesting. I mean, if it's super expensive filter, I'm not going to buy one. But
Right.
if someone in the club had one and wasn't using it, I would want to snatch it for an evening and go look at the
Yeah,
ring and dumbbell
it
nebulas with it and see what I could see.
it's making me
Yeah.
want to go to Cloudy Nights and a couple of the boards and kind of check for what they're saying, the visual guys, what
Hey,
they're
You could
saying
ask
about.
some visual guys, have you ever tried one of these filters for visual? And what did it do for you? I
Oh,
bet
I'm
people
sure
have.
there's a lot of talk about them because people have money to do the testing and
Exactly.
and
hey,
I don't,
Grant.
but it's like I say, in our day, the visual work was all single band, narrow band, and then they started coming out with the multi bands, and it just kind of makes you wonder, like I am. So anyway, thanks, man.
Yeah.
Hey, Grant. I have one of those filters if you want to try it for
I
visual.
might try it. I'll have to make a 2 inch to 1 1/4 inch adapter for it, but that's cool.
That's one of the filters that you tested for
Oh yeah,
me
yeah, yeah, yeah.
on that
Oh yeah,
spectrograph.
Cool.
yeah. Because now I'm going to be using a 2 inch in an f8 light cone, so I shouldn't have to worry about. I should think.
Yeah, there you go. Don't worry about band shift. Yeah.
You got a satellite filter?
Yes, it's called a laser to shoot them down. Thank
Well,
goodness for
I
stacking
hear you
software
guys.
that eliminates the
I was gonna
trails, though,
say,
isn't it?
yeah, you guys got all sorts of cool software tools that we never had back in the day, man. You can eliminate airplane flashing lights and satellites, and man,
I've got a question about photography. the Galaxy filter. I have a 3D printed fixture that I can attach a 2-inch diameter filter on a C Star. Is are the guts of a C Star camera, would that benefit if I'm like in a light polluted sky and I want to photograph galaxies? And there are a lot of galaxies to photograph. Um, would the C Star benefit using something like one of those galaxy filters? Would the electronics allow that? It's got a halfway decent F ratio. I think it's what, 4.5 or something like that.
The problem is this default non-light pollution filter is a UV IR cut, so it does not have a broad spectrum mode where it has basically filter wheel has 3 filters in the C Star. It's got a UV IR cut,
Yeah.
and it's got the light pollution filter, which is kind of a dual narrowband, and then it's got the darks filter, which is essentially a blackout filter. And so there's no mode where it can have a raw light coming through that has the infrared, unfortunately.
Oh, okay.
Yeah, but what people have done is they put narrower dew band filters in the front. So its filter is 30/20 nanometers. Okay, it's 30 nanometers for oxygen and 20 nanometers for H alpha. And they've put on narrow filters like someone put on like a 7 nanometer filter. And it worked. They had to make sure it was taking longer exposures. One problem is the number of stars you see. It has such a tiny little sensor on there that when you cut down too much light, you just, you're shooting from a part of the sky that doesn't have that many, inherently that many stars. You're going to get too few stars to stack. And so there's an issue there. Now, the Pro versions have the IMX 585, twice the area, more opportunity to cut down the light further. But the person who did the 7 nanometer said it worked, and he got better images, and it kind of proved that the C Stars in the future should be able to ship products with narrower dual band filters than they did. The filter they put in there is pretty conservative. I imagine it's to support shooting 10-second exposures from all conditions and still see enough stars to stack. That they didn't want to get too narrow because it starts getting a little harder, and there could be situations where they might not see enough stars. And so I think their just design was conservative.
So what part, maybe I missed something. What part of the telescope is actually cutting out your infrared? I mean, this is generally
in the C Star
for all,
or in general.
Well, for C Star, and then maybe in general, like a red cat.
In general,
or something.
it's the first filter it hits. Generally, in a mono system, it's going to be your luminance filter, and of course, all the other filters, R, G, and B, they cut out the infrared. And then if you have like a simple refractor with just a one-shot color in there, it's generally the filter. It's usually the window. There's a protective window in front of the sensor itself. And a lot of the deep sky cameras, that protective window actually is a UV IR cut filter.
Yeah, that's
what
what
you're
I
about.
was
But in some that aren't, then you have to specifically supply a filter. So you have to put a filter somewhere in your system to cut the UV IR. So you've got you have a luminance filter in your filter wheel, or you actually screw a filter on the front in your optics somewhere. So you have to provide it. But if you bought an ASI 2600 MC or a 533 MC, it's going to have a UV IR cut filter on the protection window. Yeah.
Okay. So unless you have something very special, you're going to have a window that's going to cut UV and IR.
If you have the uncooled
Usually.
585, IMX 585, the ASI 585, it doesn't have one. I have an ASI 485 and a 183, and neither of those have it. And I have a little 1.25 inch UVR cut that I just screw on the end of it, when I shoot anything except for infrared. Yeah. Well, good. This has been good dialogue.
Yeah.
So you guys are extension of your club, right? And then you meet at the club too sometimes. You have club meetings and talkers, and then you also probably have nights out where people are bringing their gear and doing deep sky.
Yeah, that's U.S. shipping, but with the $5 extra, instead of coming on a slow boat from China, it will.
Sorry about that. Yeah, we have a general club meeting once a month. It's more general speakers and things like that. Then this is the astro imaging group, and since COVID, we've still stuck with Zoom because it works and it allows us to have people like you and other people
Right.
from around the country.
And Carrie.
Yeah, some of our members are not in the area anymore or
Mm-hmm.
never were. And we also, our club's geared towards outreach. We actually have a county park that has an astronomy viewing area open 24/7. And every Friday night, clear or otherwise, people come out there and we give them views of the sky.
Mm-hmm.
We actually have a 32-inch Dob as well as like a C-14 in a roll-off building.
Wow, that's nice.
But so yeah, we can get quite a few people out there.
That's nice. Yeah, we're in downtown Portland we're at the OMSI, the Oregon Museum of Science and Industry, where we have our monthly meeting, and so it's very right in the middle of light pollution. So there's no real place there. We're kind of thinking, is there some area, the gravel parking lot? Maybe we could do something, but unfortunately, it's just so there's the closest kind of darker site is this park. That's about 45-minute drive for most people, 40 minutes, and so they have events there fairly often. Yeah. Oh,
Yeah,
good.
unfortunately for us, it's getting very bright here. Everyone that moved out of St. Louis or St. Louis County moves out into the county where we're at, and it just keeps getting brighter and brighter.
Yes.
But it's still possible to view out at the park.
Yeah. Great. And then smart telescopes being kind of the hot item for a lot of people that are kind of getting into it in your neck of the woods. For us, I see a lot of people using them and loving them. It's like a lot of the new practitioners that we get, that's the first thing they get is a smart scope. And later they may get something else stuff, but they're definitely a lot of people are starting there.
Yeah, a lot of our newer people are using those, and we found a lot of our old visual people that would never ever use a camera or do anything but look through an eyepiece have bought sea stars or dwarfs, and a lot of them use them at the same time.
Yep.
And our club has three of them that they can check, that anyone can check out, and we continue to add more.
Yeah.
And I'll probably add, with people going sea stars, primarily, there are only a couple of dwarfs out there, but with sea stars, there is the wide range of desire for how far to push it. Some people are very, very happy with just the sea star image, totally unenhanced whatsoever. And other people will say, oh, okay, well, I'll adjust the brightness, contrast, and those kinds of things. And other people will take the files off the sea star and they'll run them through something like Cyril or something like that.
Yeah, it's nice if you're a visual observer. The Dob gives you something to do between the longer exposures.
Yep.
And
certainly.
That's kind of how I use. I see there's a place for all of it. I mean, you can go out on Friday nights and do both and have a great time, or do one or the other. There's no right or wrong with it. It's all good. It's all out in the dark looking at cool stuff. And
my telescope's kind of a real long focal length, and so but my atmospheric seeing is typically mediocre, and as it is in a lot of places. And so when I'm rolling it out, it's kind of like if it's really good and there's a planet up, it's like, oh, visual time, I'm going to look at a planet, and if it's really good, then I'll take pictures of the planet. So I'll look at it first. It's like, oh man, it's really sharp, enjoy the view of the planet. Then I get the planetary camera in there. That takes, it depends on if I'm not doing an animation of Jupiter, then it's like a 10 or 15-minute thing. And then I put the deep sky camera in there and then fire up Nina on the computer, and it usually have some target that I'm working on. So then it goes off and does its job, and then I go to bed. But yeah, it's the same thing. It's like sometimes I'll start with visual because it's a particularly good night. Or if the Orion Nebula, you often just take a peek at it, or star cluster, even for my light blue skies, they can be pretty interesting. So, but
one of the things that's so intimidating about astrophotography are just the complexity and all the details. And it's kind of in the past, until it was a sea star, was intimidating, to be honest with you, because like you say, there's so much information to read, and you can read information that's just not relevant to the setup you have. And I mean, this is
Yeah.
this. I mean, this is a lifelong learning experience if you want it to be. I mean,
Yeah, and the
it's
image processing, capturing the data is complex enough, but I'd say the image processing is much more complex just because it's almost unbounded. It's almost infinite. I mean, capturing data, once you get it set up and it's working well, you're kind of done. You don't have to keep on working. But image processing, you can learn 20 tools in PixInsight, and that leaves 80 more that you haven't learned how to use, plus 40 downloadable scripts and all this stuff. And every month there's something new, and someone's promising some new technique, and and then you got Photoshop on top of that. It's almost an unbounded universe for the image processing for me. And so I kind of tell people, yeah, the capturing is can be complicated, and but you'll kind of master it. The imaging, it's kind of you're always learning. It feels like from the post processing.
So Andy, you have a C star, right?
yes, S50.
Okay. Does the C star have a built-in processing where you just, capture the image and it stacks
Oh,
it and processes it for you?
it does. It will do all of that, and then they have an A that will of a lot of the light that's not spared. It'll get rid of the graininess. It's absolutely amazing. If you were just content on using that, you
Yeah.
could have amazing photographs for so little effort and so much concern. And it's so much fun sometimes to just watch these
Mhm.
images develop over time.
Yeah.
And you have at least something to show for an evening. You're out there with the Dob. It's all personally rewarding, but at least with a photograph, I can come home and show my wife, look at these things that we saw out there.
Nice. Nice.
You know?
Thank you.
Yeah, it is the
And
built-in
everything
imaging of C
counts.
star is actually
They,
pretty good. It gets you
people
like
would look,
80% of the way.
What was that?
Yeah. But Miguel, my wife loves seeing your photos, like on Facebook and stuff. She just absolutely loves seeing that stuff.
Oh,
So,
thank you. Appreciate
yeah,
it.
I got
yeah.
just real quick, I'll show just an example of when you talked about C star. Let me just do real quick. I'll just show my desktop real quick. So I brought a C star home from the club to play with it. And I'll share a couple of my photos here. And so, this is just straight from the C star, and it's only
Wow.
42 minutes, but and then I actually processed it myself and did all the PixInsight treatment so far. So you can get definitely better. So the straight fit C star is on the left and doing all my processing
Hmm.
on the right. You get more details and stuff, but a lot of people are pretty happy with just a straight from the C star image, you know.
Yeah.
It's not bad. Um, Here's another one that's pretty straight from the C star also. So it does a pretty good job of just the basics. Um, I think that's straight
Plus,
from the
you
C
could.
star right there. And that wasn't that
Mhm.
much time. M109 is not the fab. I did here's straight from the C star. And again, it does a pretty good job of just kind of throwing the image out there. I did some processing on that to kind of do a little better, but straight from the C star. For the Rosette, I actually did the processing myself, but from the C star. But I was impressed with the C star. I thought it kind of punched above its weight. You got for a 50 millimeter little telescope that you can just pick up with one hand and just carry it around and stuff. And just from my back deck, I thought it did pretty well for that. So anyway, yeah, I thought that their image processing, built-in image processing is not bad for what it is.
Yeah, because as much as I use a Dob, there's no way I
There's
can
there's my job.
see horse head.
There's my job working at night.
And with yeah, and the C Star does a beautiful. If you image it for 40 minutes or an hour, you get this gorgeous image of Horsehead Nebula.
Yeah,
It's unbelievable.
it does a pretty good job. But,
Oh my, look at that!
You should be
what was that?
recording this,
Look at
Dan.
that thing. Oh,
What was
I'm,
that?
I'm on the phone with Dan Ladwig, and so I can't listen to the good stuff now.
Yeah, I think I never did a lot of visual, but it's just that's the way it's going. There's always going to be more and more C stars and more cameras, and
Hmm.
I'm the guy that thinks, eventually eyepieces will be a relic of the past. And
Yeah.
every version, the Chinese, the
Mhm.
craziness of how quickly they come out with stuff, and by the time we're done with this, there'll be the C Star, the 30 Pro or whatever be out, or and then 6 months from now there'll be a new version that's even better, and it's going to be amazing to see what they have in a year or
Yeah.
two.
Yeah.
Yeah, I did a kind of rough costing analysis of what the Pro should cost. Although component pricing are really throwing the monkey wrench in it. But CSOC Pro should cost about $899, and it would be an IMX 585 sensor, so you have a good wide field of view. It has the quadruple, so it has the field flattener. But they say it's going to be about 1,000, about $100 more because of component price increases when it comes out in the
And
late fall.
which sensor will be in that?
It'll be the 585, IMX
Oh,
585
really? Okay.
sensor. That's what's in the S30 Pro, which
And is that
costs
a,
$649, I think.
and
Yeah.
will
So
it be a mono sensor or color?
color sensor.
Color.
So
Okay.
um, yeah,
Isn't the
I actually
That's
585
50 Pro sometime coming up.
isn't the
About
isn't the 585 a near infrared sensor? I read that somewhere.
here, I'll show you real quick, just a comparison of the telescopes that I expect.
I,
So,
I just put up a screen there, so you won't be able to do it. But
oh,
really
okay.
quickly, about a month ago, Bill had this down to his place in the country,
Oh, there you go.
and it's perfect time for it was at that point perfect time for Messier Marathon. And I thought I'd try to do as much of a Messier Marathon as I could with my Sea Star. And so I limited my exposures to like the Sea Star shortest in a plan, which is 10 minutes. And I ended up capturing 56 Sea Star objects that night. And that's obviously M8. And that was 17 10-second exposures,
Isn't that
Hmm.
great? Yeah.
Hmm.
in stack. Now, admittedly, M8 is it one of those wonderfully bright, cheaty kind of objects
Yep.
in the sense that there's plenty of light there to do it.
Yep.
But ultimately, 56 Messier targets in one
And
night
whatnot. Yeah.
based on you could only do 6 per hour. And so that's how it
That's
kind of
that's a great contest.
Hmm.
Yeah, I went out on Astroband and found the best C-star images, and then I looked at them, the equivalency for a similar size refractor, it's similar Bortle, similar amount of time, right? And both of them did the pix inside, they stacked and so forth, and the C-star images were just a notch below, but real close. And part of that was because for every one C-star image that had those conditions, I could select from 20 standard rigs just because there's so
gotcha.
many more. This was C-star's kind of new. So wait till C-star gets more mature, more people on it, and so forth. It's fairly competitive. I was going to share one thing that you mentioned that this is just a chart that kind of shows the different scopes, and you mentioned what the C-Star Pro has. So I outlined the pros. So what they did with the Pro is they went from a three element to a four element refractor. They added the field flattener. The reason is they went to the larger size camera with 4x the area, the 585, and because it has such a larger area, they needed more correction across a wider field. So they added another element to the telescope. And then, so that gives you a really huge field of view, 4 by 2.2. Then they added an 8 megapixel secondary camera with a secondary lens for Milky Way. So it can also do Milky Way shots. So it's a completely second optics. It's a little tiny lens on the very top there. If you look at the C star, you can see a little dot at the top there, and that's the second lens. And that's for
Hmm.
doing Milky Way shots. And they have a bunch of software in there for compositing the background, the mountains and stuff with the stars, so they can kind of keep them separate. And
Hmm.
so that's the Pro. And what they're going to do with the C Star Pro is the C Star S50 Pro will do the same thing. They're going to include the elements, four elements. They'll get the 585 sensor in there. So they'll have a wide field of view. I'm not sure if they'll add this is my guess. They'll add the wide field, but it's really popular in the C-Star 30 Pro. So maybe, maybe not. And at this time I said 799, 849, but I would say like right now it's going to be 899 to 1,000
Yeah.
because component pricing increases. But and that's supposed to come out at the very end of this year. The
Oh,
CEO is
really?
actually using a Pro right now. It's S50 Pro. He says he's using it. He's been using one, so he's taking it with them. So he has one, as one of their prototypes. but it's not out yet. They're not selling the C-Star S50 anymore. They're basically trying to lower their inventory of those right now. And when they get those cleared out, then I think that will leave the room for the S50 Pro to come out. That's
And
what they said.
they're not selling them on the website. Gina Astro's out of them. So yeah.
Yep. Yeah, this one
Five
is
points
basically
out.
can't get. Yep. Yep. So expect this S50 Pro to come out. It's probably $100 more than I'd kind of hoped, just because component pricing. But I looked at some of the components, like the 256 SD used to be $15, and now it's $60. Just and so some of the components have really gone up with the all these AI server build outs have really put the pressure on RAM and SSDs and some other components, and so it's going to affect the price of all the things we buy, including these smart scopes.
Yeah.
Anyway, yeah, so that was just a chart I put together, just kind of keeping track of the smart scopes that are out there.
And I will smile and say I'm addicted to astronomical league observing programs. And so I did do the Imaging Messier and Imaging Caldwell from the beautiful confines of Chesterfield, Missouri, with our Bortle terrible skies. And it works.
That's good. Did you do it in program mode? Like have all these targets all programmed up?
No, I
You went
didn't.
kind of manually each
No,
one, like go to this
I
one, go to
figured
that
that was
one.
too cheating to do it that way. And it's a case where I mean, I know how to do a plan. I can do a plan, but it was like for that, no, I don't want to fall asleep in the middle of the night.
Right. That's good. Yeah, I think I was really impressed borrowing the C-Star and setting up just this little thing. It's next to my 100-pound Dobsonian. Yeah, my Dobsonian collects light several times faster and it's more detailed. But man, for the weight and the size and the cost,
And you can
it's
see color.
it's pretty amazing. Yeah, and for visual, yeah, I mean, I was a visual guy with my Dob for several years before I ever stuck a camera in there, and even at very dark skies, I mean, I know there are people who are super into it, but for me, I tried really hard to love finding, galaxies and star clusters, and there was a few wow objects. There were a few objects that definitely made you go wow, but there was a lot of them where it's like it was just the hunt to see it, and I can kind of see it, see that little smudge, that's a galaxy, and it just didn't. And then when I started doing astrophotography, it's kind of like, oh God, that feels so good. I can really see it. So I must admit, I got kind of spoiled with astrophotography.
Yeah.
Yeah.
Yeah, I think
Yeah, the
there
Virgo
was one
cluster get kind of patchy. Yeah.
there was one night where Steve and I went out to some dark site and he was working on the Herschel list or something, looking at little bitty fuzzy galaxies.
That was Whiteside.
Yeah. And I was taking pictures and he's, my stuff, like you were saying with astrophotography, I've been doing it so long. I go out there, set up my stuff, and it just works. I'm not automated, but I mean, it just works. So I love viewing through other people's Dobs and stuff like that. But it's like one little fuzzy area after another. And even Steve was saying that at the time.
Yeah.
And,
I did
Dan
have one.
said, this is a quote. Is it that fuzzy thing in the middle?
It always is. It's always the fuzzy thing in the middle. I did have one moment it was like 6 or 7 years ago, before I ever bought a camera. I had an exceptionally clear scene night. It was the best scene by far ever. And I was setting up to look at Jupiter and Saturn. They're both up together, and Saturn and Jupiter were just amazing. Saturn was just like it was like looking at a Damien Peach photo of it. It really was. It was just amazing. It literally looked three-dimensional. It looked like it was floating within the rings, and the shadow of the rings casting across the planet, and the gaps in the rings, and you can see the bands on Saturn, which are harder to see. You can see them, and I just couldn't stop staring at it. It was just, and that was better than any picture I had taken Saturn. Now, I didn't have a camera at the time. That would have been a great picture, but I must admit that Saturn on a super good night of super good scene in a large telescope was pretty amazing. That was an amazing viewing experience. So that one right there is kind of super memorable. And I'd say Orion Nebula, a couple of the bright nebula on dark skies and some of the big star clusters can be pretty nice in a really big scope.
I like open star clusters with a Dob. I mean,
yes, they're better than the pictures.
Yeah, they're. I mean, any Dob with an open star cluster is.
Yep. I must admit,
wonderful.
stars are pretty in Dobbs. They're just so sparkly and vivid. You can't replicate that in a photo. They're
No.
they like they're like burning into your eyes. You don't get that with a photo. They're just, you look at it, a big dot especially, man, stars are
Yeah.
bright. Look at Sirius in a 20-inch dot. It's like it hurts.
Yeah.
I live in Colorado and we were up in Wyoming last year. One of the guys in the club I'm in has a 30-inch Dob, and we were at 9,000 feet on a really nice dark skies, and we were getting color visually in the Veil Nebula.
Wow. That's amazing. Yeah.
Yeah,
So
I still
yeah,
remember one night I went out and we were somewhere in Arizona and we could see some guy had a really nice refractor at the time, but it was a really big AP one, and you could see the blue color really easily in the Pleiades, which
Oh yeah,
really shocked
yeah,
me. It
with a
was,
dog too.
yeah,
yeah.
really amazing. It
Yeah.
was as good as most photos I've seen.
Yeah.
Even in
That's-
Danville with the Dob, Pleiades is blue. It's gorgeous.
Hey, does the club have that? I know there are two different types. One's like a night vision, and then the other one's a smart eye. I know Tan has a night vision that he attaches to a dog. Have you ever seen that, Dan?
Yeah, we don't have either of those.
Okay.
Actually, advertisement. I believe they're going to give away. We have the Misrael, the Mid States Region Astronomical League conference coming up that we're hosting.
Yeah, that's what I wanted to ask.
One of the door prizes is one of those smart eyes.
The Pegasus one?
I believe so.
Okay. That's another question I wanted to
and
ask.
a dwarf mini.
Okay. Who in the club is going to that this year?
I would assume a lot of people just because we're hosting it.
Are you going, Dan?
I
don't want to put you on the
probably.
spot. You know
I'm
what?
on the
Don't
committee
an-
for
don't
it,
answer.
so
Don't
probably.
Don't answer. Yeah, I was looking at my available schedule after some projects I'm through working on. I'm like, June. Okay, I might be able to swing a Saturday. It's a Saturday. Is it
Saturday,
Friday,
Sunday,
Saturday?
Friday
night,
Saturday,
Saturday, and always
Okay.
till noon on Sunday. In
Yeah,
different locations, different days.
Yeah, as far as I know, no, the club doesn't own any of the night vision equipment, but several people do.
Okay.
Amazing stuff. And if you look through, search for ASEM on YouTube. During COVID, I actually had someone that did a presentation on using night vision for
Okay.
imaging and stuff like that. That was really good.
Thank
And
you.
after we set that up and he gave it, we sent that out to the Astronomical League, and then they said, oh yeah, you can use night vision equipment on lots of observing programs.
Excellent. I'll give
Yeah,
them
just for
link there.
Steve Berner heads up several observing programs, and I head up the imaging observing program for the AL. So
Yeah.
we're big into AL programs. Astronomy merit badges.
No,
Yes,
They
that's
have
all
that
merit
in
badges.
our kind of club too, giving the merit badge. Yeah,
Nice.
like Pokemon, you want to collect them all.
Have you, Stephen, have you been to Dan's Flickr page?
I don't.
Yeah,
Oh, I don't know.
yeah, Dan is just like next level with his work, man, and just his output is just it's like every day. It's like, man, where does this guy find time to sleep?
I'll have to check it out.
Yeah, but I know he's doing remote stuff.
There are
I know
some
you're doing remote stuff.
there are some people that spend lots of time processing, and then there are other people that process their images the same way they did a decade ago. But
Yeah.
I
Yeah.
have hundreds of images published in magazines and books and things like that. So
Yeah.
that's just the way I work.
Hey, Dan, why don't you get a big file of one of your images and send it to everybody, and then we can all see what we can do and see how different everything is going to look. And then we can talk about each other's images.
It's a good idea.
Let's get something simple, I might have it colored up like looks like something you'd see a kid with a box of Crayola,
Anyone have any more
Get into
questions
the
on
Hubble
filters
palette.
for Stephen?
Any more filter questions or any questions about shooting with a Dobsonian or anything else?
Yeah, I'm going to find your chat on, you said the Astro Imaging channel, right?
Yes. I can post a
Have you
link
given more
here.
than one talk at that?
Just one.
Just one. Okay.
Yeah.
Yeah, that's an interesting channel. They have some pretty nice presenters. I think they was it Sunday. They had one about PixInsight. So I don't know if everyone here uses PixInsight, but PixInsight has this new. I don't know how new it is. Maybe a month, maybe 2 months. Pixel Math UI. So a lot of the scripts from Bill Blanchard, someone else, I can't remember. They've kind of all put it into this one container, if you want to call it, Pixel Math, Color Mapper, Norband normalization, and it's all in one, like I said, in one pod, and that thing looks impressive.
Yeah, I pasted the video on the link on the chat
Okay, great, thank you.
for those that are interested. But
Yeah.
yeah, and if you want to send that out, Dan, you can. But yeah, about a year after starting imaging with the DOP, I got invited to speak just because people just didn't know it was possible. And essentially, it's what makes C-stars possible. It's the same fundamentals. It's low read cameras, fast computers. Low read noise cameras, fast computers, and using plate solving to direct where the camera goes. So those three fundamentals allows simple systems to do deep sky these days. And there are trade-offs, but it does it well enough that I think people thought it was kind of impossible, and now they realize, oh, okay, it is possible. So it was news 3 years ago, certainly, that you could do it. And now with all the smart scopes, I think people kind of realized, okay, it's definitely possible to do. I think that for me, the Dobsonian, the main thing that made it really possible was I didn't realize it could be controlled from Nina. I can totally automate it. I used the hand controller, and it could go to an object, and you put in but it had a USB peripheral import in the bottom of the hand controller. I never knew what it was for. It turns out that, you can plug that in Nina, and, with the right driver, it sees it as a fully automatable telescope, and it can go to any target in the sky, and you can sync on targets, and it updates its plate solve and guiding, and it's not guiding, but it's tracking. And that was something I just was new to me. When I bought it, I never knew it had that capability. So that's what really enabled it.
Did you ever use a focal reducer with yours?
I did. I have the Nexus from Arizona. So
Okay.
my f4.9 is f3.65 now.
The reason why I'd asked that is that long, long ago I tried to do some imaging through a 12-inch diode, and I could and I needed a focal reducer. I could never get it in focus. Well, it turns out it was one of those Skywatcher collapsible ones, and it
Mm-hmm.
took me forever to realize that all I had to do was not extend the tube all the
Yeah,
way.
just shrink it a little bit. That's
Yeah.
right. Just not quite put it all the way up. In fact, Skywatcher for a while had indents at a position that allows you to lower it a few inches. And the purpose was not for that, but was for bino viewers. Because bino viewers required a lot of back focus. That's the bino where you put that in and you have two lenses and you can look through it like this. And so that allowed you to do bino viewers. And then people said, oh, this is also good for astrophotography. Yeah. Yeah, the same thing with the Nexus. The Nexus requires 55 millimeters of back focus. I didn't have that, but the Nexus fits all the way into my focuser. So in fact, it started to intrude into the actual light path in my telescope. So I actually mounted my mirror forward. I got some little longer springs and some little nuts, and took my mirror off and mounted it about 20 millimeters up the tube, and that pushed the focal length, the focal focusing point 20 millimeters out. It's kind of like me sure it's a solid tube. I can't do what you did, was lowering the struts. So I just pushed the mirror up a little bit, pushed it out, and then my focal reducer, the Nexus, doesn't intrude in the light path. It comes almost into the light path, but not quite. So I did have to tweak the scope a little bit. It wasn't a big deal. It caused a little oblong spike on stars that are near the edge of the field. It wasn't a huge issue, but it did solve that issue. So. anyway, thanks again for inviting me. And anyway, I have a list of talks I had given to the club, Dan. If any of those others are interesting to people in the future, we can always, do it again, So,
Oh, yeah, okay. Um,
Thank you,
Thank you.
Stephen.
Yeah.
Appreciate it.
And join us at any meeting. We're the third Tuesday of every month.
okay, that's good to know. Thank you. Yeah, happy imaging, clear skies. I'm gonna log off and good night, everyone.
Good
Good
night.
night.
Thanks for doing
Take care,
it.
everyone.
All right, bye-bye.
Hey, thanks, Dan, Grant, everyone. Good seeing you, Randy, Steve.
I'll see everybody.
All right, take
Bye,
care.
ya.
Bye. Bye, Grant.